Hi, everybody. And I am Doug Schmitt. And I'm a lawyer at Alexander Holburn in Vancouver. I'm fascinated by meteorites and the laws about them. This has taken me to many interesting places and to many interesting situations around the world. For example, I gave a presentation at a conference of the Meteoritical Society at the Pontifical Gregorian University in the Vatican. The Vatican has one of the world's biggest meteorite collections. The Meteoritical Society is about 1,000 scientists in 50 countries. They do the real cutting-edge scientific research on meteorites. They have a working group. They're drafting a code of ethics for the collection and distribution of meteorites between scientific institutions. And I'm on that, drafting the code of ethics with someone from the Smithsonian, someone with the Natural History Museum in London. These are some of the world's biggest meteorite collections. So why would anyone be interested in meteorite law? Well, did you know that people have gone to jail for illegally exporting meteorites? There have been diplomatic complaints at the highest level between one government and another, complaining that a meteorite illegally taken from one country ends up being the subject of scientific laboratory research in another country. So there's all kinds of serious problems that they face. Most meteorites are found in Antarctica, on the ice. Who owns those? The answer is very similar to the law of the high seas, which is what I do for my day job, transportation law. And I'm passionate about that. Meteorites have a lot of value. They're priceless scientifically, and they're very rare. So this has generated a black market into which meteorites are illegally sold, and then they become unavailable to scientists. So the lawyer in me is saying, yes, we should do a TED Talk about that. But no, management here said, that's too boring for TED Talks. So tell them something interesting. So that's what I'm going to try and do. Now, has anyone here seen the movie Armageddon? What, a giant asteroid approaching the Earth? Well, that movie and everything you learned about meteorites in it and most science fiction is completely wrong, and I'm here to set you straight. Okay. Most meteorites are samples of comets, asteroids, and pieces of Mars and other places where we have never had any scientific samples returned by space missions. And none will be returned from them in our lifetimes because of the huge cost. The problem with meteorites is that we don't know enough about them. Did you know that your chances of being killed by a meteorite are about the same as dying in a plane crash? About 1 in 20,000. Your chances of dying of food poisoning are 100 times less. Now, the assumptions here, obviously critical, are that the asteroid is 2 kilometers in diameter, and as we'll see, that's quite normal, and that 100 million people die in the impact of that asteroid. In fact, the 100 million figure sounds horrifyingly high. It is. But it could be much higher than that if the asteroid impacts a highly populated area, say Asia. If it lands in the ocean, which is quite likely, a tsunami created by it would wipe out the coastal low-lying population and that's where almost everybody lives in the world. So these numbers are shockingly real. There are lots of asteroids out there, many, many asteroids, and most of them are unknown. We're trying to keep track of them. This is a chart done by the Minor Planet Center at Harvard University. Every day they publish one of these, and what we're looking at here is the asteroids that they're following. The ones we're concerned about, the potentially hazardous ones, are defined as asteroids that are in orbits that intersect the Earth's orbit, not necessarily when Earth's there, but cross it, so they'll continue to do it once in a while in the future, or ones that come quite close to it, 5% or so of the radius of the Earth's orbit. So that's not all of the asteroids. It's the ones that are on courses that threaten the Earth, and also the hazardous ones are you only count them as hazardous if they're over 100 meters in diameter. So the red dots here are the potentially hazardous asteroids. As of this morning, there are 1,338 potentially hazardous asteroids that are being tracked simultaneously, or as resources allowing, by the Minor Planet Center at Harvard. And every day, another potentially hazardous asteroid is found. New ones are entering constantly. The green dots are the asteroids they're checking or following, which are not considered hazardous. In other words, they're in orbits that at the moment are calculated not to get to Earth, crossing Earth's orbit or too near it. There's the difficulty of keeping track of them, of course, is huge. It's an immense calculation. There are only so many telescopes that are involved in this study. Resources are limited, but this is where they've gotten to in a study that's been going on for about 10 years now. The orbits that these asteroids are in, some of them are circular. Just to understand this chart, the orbits of the planets are shown in blue. The closest to the Sun is Mercury, then Venus. The Earth's in highlighted blue, and out beyond that is Mars. The solar system is much bigger than that, of course, and so there are many other asteroids beyond Mars. But this is just to give you a sense of the close-up picture of this problem. Trying to calculate and track these asteroids is a huge problem. Some of them have orbits that are quite circular, easy to predict. Others very elliptical, so they come zipping in from far out in the solar system, around the Sun and back out, crossing the Earth's orbit twice. Many of them simply appear from a random direction, quickly approach the Earth's orbit, and then head off in some other random direction. So it's a huge amount of work keeping track of them. It's very similar to trying to trying to calculate the position of a bunch of rocks moving around in a cement mixer. Well, so what, you say? Well, did you know that once a month, on average, the Earth gets hit by an asteroid that explodes in the atmosphere with the force of a nuclear bomb? We know this because satellites have been up there looking for illegal nuclear testing for decades, and they keep getting false alarm signals, which we now know are asteroid impacts in the atmosphere. So we have a good track record of how many there are. The worst one in the 20th century was in 1908 in Tunguska, Russia. And this rather bad quality photograph shows what the devastation area looked like, and it covered hundreds of square kilometers. A Russian survey crew in the 1920s published this government report, and it shows how the trees are knocked down in a certain angle. And they surveyed hundreds of square kilometers and then put all the data together, and that allows them, and especially us now, to determine how strong the explosion was and what would cause damage over this huge area in Russia. That was 1908. Just imagine what would happen if this occurred during the modern nuclear age without warning. I suggest it would have triggered nuclear retaliation, World War III. To try and make some sense of all of this information, we're going to develop the information we have now. First of all, the Earth is constantly being hit by a rain of small asteroids, small meteorites that do very little damage. The big dangerous ones that we should be worried about start to be in the annual event, 20 kilotons, which is nuclear explosion size. We have a lot of information about these asteroids from the geological record. So we've got the satellites in space, but also on Earth, when there's an impact of an asteroid, it shocks the rock that it hits, and it makes a very characteristic kind of mineral structure that geologists interpret as shocking caused by asteroids. And there are hundreds of these circular impact structures which can only be explained by being asteroid impacts. And the good news is we can date them radioactively, so we can get a track record of how long ago a lot of these impact events happened. So trying to pull all this together, we have the annual event, 20 kilotons. Tunguska, that was in 1908. That seems to be the 1,000-year event based on the geological record and just putting all of this together. Note that the diameter of the asteroids is on the bottom of the chart, and Tunguska is a 50-meter asteroid. That is only half as big as it needs to be a red dot on the chart of potentially hazardous asteroids. So if Tunguska was out there right now, headed this way, it wouldn't even rate being a red dot. The big one in the geological record is the Chicxulub meteorite crater that landed in Mexico about 65 million years ago, and which probably drove the dinosaurs into extinction. Very rare. The bigger they are, the rarer they are, fortunately for us. But here's a chart. It's based on analyzing the geological evidence as well as the astronomical evidence. The size of Chicxulub is 9 kilometers, which is about the size of downtown Vancouver, half the size of Manhattan Island, roughly. The 2-kilometer asteroid that we're talking about, as an example, estimated to kill 100 million people, is more common than Chicxulub. It's not extremely likely, but it's definitely part of a continuum. It's happened before, and when you look at what the potentially hazardous asteroids are that are cataloged, there are some in that range. So we may not be facing one of these problems today, but inevitably our civilization will face this risk. Now, there are many different types of meteorites. They're not all the same. Some are made of stone. Some are pieces of iron, like this one. This is a nickel-iron meteorite. It formed in the solar system between Mars and Jupiter. It is part of the core of a planet that never quite happened. So it's like the iron core of the Earth, except it's all smashed to pieces. It solidified on Earth, it solidified up in the asteroid belt around 4 billion years ago. So this is older than any rock on the Earth. It landed in Odessa, Texas, 50,000 years ago, and was quite recently, and at some cost, legally imported into Canada. Okay? Got that? Yeah. Now, when they land, they can do a lot of damage. I've always wanted to do that. Okay. This is the only meteorite that has ever fallen to Earth twice, and you saw it here on TEDTalks. Okay. I don't care if I have to pay for the carpet. It was worth it. Now, remember Armageddon. The asteroid there was the size of Texas, according to the script. And that's quite a bit bigger than Chicxulub, right? Texas is way bigger than 9 kilometers across. But here's where things go wrong. In that movie, the heroes blow the asteroid cleanly in two, just as it's about to hit the Earth. And one half of it goes on one side and the other half on the other, and everybody is saved and lives happily ever after. Well, unfortunately, it just doesn't work that way. The truth about asteroids is that they're largely unconsolidated, weakly consolidated piles of gravel moving along. So if you try and push on one of them, suppose you had a rocket and you put it on the asteroid, you want to push it out of the way from hitting the Earth. You start pushing on one side, and your rocket is just going to go right through the asteroid and out the other side. It doesn't make any difference. It's not going to change its course. Nuclear explosions would be, which did the trick in Armageddon. Okay, if in an emergency, we'd have to try it, but it's very risky because it's quite number one, the asteroid would probably just disaggregate and then pull back together again and continue going its merry way. Number two, it would quite likely expand, become a much bigger cloud, and hit a bigger target area on Earth. Right? So it's not going to solve the problem. You're just making the problem worse. So what do we do? We've got some technology it's in the theoretical stage, but work's being done on it. And there are a couple of practical solutions for when we inevitably face this safety risk. One of them is the gravity tractor. The other is the Yarkovsky Effect. Reverb, please. Yeah, okay, great. Okay. A gravity tractor works like this. You have to start years before the thing is going to hit the Earth. But you place a large mass beside the asteroid. As long as you can put something there that's big enough to have gravitational pull, it'll really slowly change the course of the asteroid so that it moves. A tiny change at an early stage can make a huge difference. It'll cause it to miss the Earth. And the way that, the good news about the gravity tractor is that it works on all of the little teeny bits in the asteroid. It pulls them all together. It doesn't make a mess of the thing. It just slightly shifts it. So if we have enough time, we can try that. The Yarkovsky Effect is very, very cool. It is based on the idea that if you paint one side of the asteroid white, it'll change its course. And this is because most asteroids are almost completely black. Put titanium dioxide powder, bright white, on one half of it, and it'll change the way it reacts with sunlight. Sunlight will heat the dark side more than it heats the light side. So one side of the asteroid becomes hot compared to the other. The side that's hot gives off more light energy, more thermal light energy, than the other side, which is cold, and that creates a tiny pressure from one side of the asteroid to the other. So the sunlight does all the work. That tiny pressure forces the asteroid away from its initial course to hopefully a safe position. Well, so that's the way of the future. What we need to do is fund more research in meteorites, which are ground truth about what asteroids are. It's our only way of finding out what they are. And we also have to fund more research in avoidance, detection and avoidance of asteroids. So if you are so lucky as to find a meteorite, before you try and sell it, probably illegally on eBay, remember it has lots of friends on their way following it right behind. Thank you.